Okay, we've talked about 1H NMR in quite a lot of detail. Um, Now we want to look at 13C NMR. Right, so we've seen that 1H NMR that told us about hydrogen environments, okay, in a molecule, and 13C is going to tell us about carbon environments, okay. Um, Now the problem with 13 with carbon is the most common isotope of carbon is carbon 12, and that does not give, when you have an even number of nucleons, you don't get an NMR spectrum. So carbon 12 can't be looked at with NMR. Now, 1 in 100 approximately carbon atoms is carbon 13. That will give a spectrum, and so that can be used to investigate molecules. There's obviously going to be a problem here in sensitivity because it's only 1 in 100 of the actual carbon atoms in the sample are going to be responding, giving a signal. So technically it's more difficult than 1H NMR. Let's have a look at a 13C spectrum and just see what we can glance from it. Right. Okay, so here, this is the spectrum of what we've got as an ester there. This ester is called ethyl ethanoate. And let's see what sort of things we can see. So probably the first thing you notice is the ppm scale. So the differences here, the ppm scale are much larger. So it's going up to about sort of 200 ppm, whereas in 1H NMR, the highest there is when you have is about 12 ppm, which is a carboxylic acid hydrogen, and most of them are way lower than that. They're like 5 ppm. So that's one major difference. Another thing which is not which is fairly immediately obvious, I suppose, is no splitting. Okay, you don't get splitting of the peaks in 13C spectrum, and the reason for that is because in order for splitting to occur, you'd need to have two carbons 13s which are next door to each other. Okay, and of course, because it's only 1 in 100 carbon atoms that that is carbon 13, the chances of that happening is not very great, and so you don't get any splitting. So you don't get as much information as you do from 1H NMR because, of course, no splitting. Right. The third thing, which isn't immediately obvious, is I want to say here is you have got 4 carbon atoms. 1, 2, 3, 4. You've got 4 different carbon environments, and we've got 4 peaks. That's good, but then the heights of those peaks should be exactly the same because they're in equal abundance, and the reason they're not the same height, and that so unfortunately the integrated values in 13C, and I don't know why, are unreliable. Okay, you can't use it to tell you, about how many carbon atoms you've got in an environment there. So that's the 3 differences. Let's have a look at some of the similarities then. Well, this chart here is what you get on the other side of your periodic table in an exam. So you get given these ppm data. So let's just have a look at these. Now you can see whenever it's very similar to 1H NMR. Whenever you're near to an electronegative element like oxygen, like this one here, the ppm is much higher. So the carbon which is attached to double bonded up, to the carbonyl carbon has got one of the highest ppm values, whether it's in esters or in aldehydes and ketones. If you are like this carbon here, you are next door to the carbonyl, then the ppm isn't shifted quite as much. It's around that area there. You may have noticed also there's an awful lot of overlap in these values here, so it's not always possible to say, oh, that carbon is definitely this, that peak is definitely correspond to that carbon. It's not always possible to do that. So the information is not quite as definitive as you get with 1H. And an awful lot of exam questions, most of the exam questions, if you look at them, they'll give you a compound and they'll just, like for ethyl ethanoate, for example, and they'll say how many peaks. It'd be as simple as that. How many peaks would you get in that spectrum? And so the questions tend to be a lot easier than the 1H NMR questions. Anyway, let's see what we can glean from the ppm values of this spectrum. We've got ethyl ethanoate here. Right, I've got one peak which is way higher than the other one, this one here, so this has got to be the carbonyl. If you look at the value here, so esters or acids 160 to 185, it says, okay, 160 to 185, that one there. So that's almost certainly this peak here. We've got another one which is a bit higher than the other ones. This one here, it's 60, and that is probably that carbon there. If you look on the chart here, we've got alcohols, ethers. This one, alcohols, ethers, esters, yeah, between 50 and 90, so that's that one. And then these two low ppm ones here, these ones around 20, they are probably that one and that one. Which one is which is not really going to be clear. I suppose you might think, right, this one would be a little bit of a higher ppm because it's near to the carbonyl than this one, which is further away. But yeah, I don't think you can definitely say which one is which there. Okay, so let's have a look at another spectrum. This time it is another 13C. This one is for butane-2-one. Butane-2-one, so we've got CH3. Oops, sorry. Don't really know what I'm doing there. That's better. Okay, so butane-2-one. Right, obviously the this one at 210, that is the aldehydes or ketone carbonyl, very high. This one here, I would guess, would be the lowest one because it's furthest away from the electronegative oxygen, and then the green one and the blue one. Well, I don't think we can really say which is which, but certainly these two peaks in this area here. Okay, once again, you can see with the heights of the peaks, they should all be the same because you've got the same abundance of carbon atoms there. They're not. So that would suggest the integrated value isn't reliable. Okay,